All right, here we go. This is problem number 91 from chapter 6 of the Halliday and Resnick textbook. So it says a block slides with a constant velocity down an inclined plane that has a slope angle theta. The block is then projected up the same plane with an initial speed of v naught. A says how far up the plane will the block move before coming to rest, and B, after the block comes to rest, will it slide down again, and give an argument to defend your answer. So here we go. This is a good one. There are no numbers in this problem, right? So check it out. There are two bits of information. This first sentence is telling me some stuff about the block sliding down the ramp. So here's how I'm going to interpret that. Here's my ramp, or my box. It's got a mass m. This angle here is theta. All right, I automatically know that there is a perpendicular component to gravity, which is mg times the cosine of theta. And I know there is a parallel component of gravity, which is mg sine theta, right? I know there's a normal force, which is mg cosine theta. That is the sloppiest mg cosine theta ever written. Let's clear that up so that you can actually read mg cosine theta. All right, now what other forces are there? Well, let's see. It doesn't say that it's frictionless, and I know that it's moving at a constant velocity. That means that my net force has got to be 0. And I know that it's sliding down the ramp with some velocity, so that means that my kinetic friction has got to be exactly big enough to make my net force 0. Aha! So my kinetic friction is mg sine theta. It's got to be to make my net force 0, right? Okay, so that seems like useful information. Now, if you want, you could go through at this point and you could find your coefficient of friction, which is definitely worth doing. It turns out to be the inverse tangent of theta, if I remember correctly. Yeah, I think that's right. But that's not what we need to do. So that's that. Now, remember, your force of kinetic friction is a fixed value, right? It's dependent on the surface and your normal force. So what's happening here is in the second part, it says the block is then projected up the ramp with an initial velocity of v0. So now we've got our block sliding up the ramp. So we're going to have an fg perpendicular and an fn. Those guys are going to cancel out. My parallel component will not have changed. It's still going to be mg sine theta. But now the block is sliding up the ramp with some initial velocity v0. But because it's going up the ramp, kinetic friction doesn't want it to, so kinetic friction is going to go down the ramp. But your kinetic friction is still the same value. We've still got the same normal force. We've still got the same coefficient of friction because it's the same block on the same ramp. So my coefficient of kinetic, or my force of kinetic friction is also going to be mg sine theta, because that's what it was here. So that means that my net force while the block is sliding up the ramp is 2 mg sine theta, right? Remember, because the block is being projected with some initial velocity, that's implying that, you know, you've got a starting velocity, but after you get that starting velocity, there's no force pushing it up the hill. All right? So there's my net force. So it's moving up the ramp with some initial velocity v naught. All right? Now, the acceleration of the block then is net force divided by mass. Aha! So that means my acceleration is 2g sine theta, right? So both gravity and friction are slowing it down. And I guess I should be more specific at this point. I know it's going to be slowing down, right? So this is going to be negative style, right? Because either my velocity or these forces have to be negative. So I'm going to choose to make up the ramp positive and down the ramp negative. All right? So now we want to find out how far the block is going to go up the ramp. So let's write down the stuff that we know. Let me clear up the board here a minute. All right, so here's what I know. I know that my initial velocity is v naught. I know my acceleration is negative 2g sine theta. And I know that I'm trying to find out how far it's going to go before it stops. So my final velocity is going to be 0, and I'm looking for displacement, right? So hopefully you are thinking about this equation. 2a delta x equals v squared minus v naught squared. Sorry, I'm still so used to using vi and vf. All right, so let's plug in our numbers. Let's see. So 2 times, oh wait, I know what my acceleration is. That's negative 2g sine theta times my displacement equals 0 squared minus v naught squared. So let's see, the 0 squared goes away. My negatives are going to cancel, divide both sides, and you get delta x equals v naught squared over 4g sine theta. All right, so that's part A. Now, B wants to know, after the block comes to rest, is it going to slide down the ramp again? Okay, well, after the block comes to rest, here's the deal. Here's the block. We're going to have our FG parallel pulling down the ramp. I don't know why I'm using this stupid fat green pen again. mg sine theta. All right, and so the thing that's going to, if it's going to not, so it's at rest right now. For a brief moment, it's at rest. So static friction is going to try to stop it. Well, remember, you guys, in general, static friction is usually bigger than kinetic friction. And since our kinetic friction was mg sine theta, our static friction is going to be at least that big. And so that's going to keep the net force at 0 and prevent the motion down the ramp. Okay? So there you go.